Hello students, in this video we'll construct a general solution to the Bessel equation of order 0. Let's recall the Bessel equation of order 0 is x squared y double prime plus x y prime plus x squared y is equal to 0. And in the previous video, we constructed one solution to this. One solution of this j0 of x was the sum, n goes from 0 to infinity, negative 1 to the n over n factorial quantity squared, x over 2 to the power 2n was one solution. We would like to find the other linearly independent solution. Now for this, what I can do is I can actually do the following. I can eliminate one of the x's here by writing this as x y double prime plus y prime plus xy is equal to 0, because I still preserve the structure of the regular singular point at the origin. Okay, so now what we're going to do is we're going to define an operator, define a differential operator, L of f. And what is this going to be? This is just going to be d by dx, the derivative of x f prime of x plus x f of x. So in other words, y will solve the Bessel equation, so y solves, let's call that star, if and only if L of y is equal to 0, okay? And so this differential operator satisfies a particular relationship. It comes from Sturm-Liouville theory, and we'll talk about that in further videos too. We have this Lagrange identity. Okay, and so what does the Lagrange identity say? It says that f L of g minus g L of f is d by dx of x times f g prime, that's be a g prime, minus f prime g. So you can easily check that and see that it works, okay? You would simply just multiply all these things out. Clearly what's going to happen over here is that clearly this x term over here, if I have f times L of g, that's going to involve an x g of x, and I'm going to just subtract off the same thing over here. So all you have are these derivatives over here, and when you expand out the derivatives, the cross terms cancel. So it's easy to verify this relationship over here. All right? And so now what I'm going to do is I'm going to take, in this identity, take f to be j0, and take g, we all know that's a solution, g to be y, just any solution. Of star, okay? And of course, what will happen if we do this? Well, then the left-hand side is going to be 0, because what we have over here is we know that that g is a solution, so that term is going to vanish. We know that f is a solution, so that's going to vanish. So what we have over here is we have d by dx of f times the quantity, and then I'm going to have a f is j0, so j0 of x times y prime minus y times j0 prime of x is equal to 0. So in other words, there is a constant. So there's a constant. There is C1 such that what? Well, now what is this thing over here really? So what I'm going to do is I'm going to put in a factor over here. We can add in a factor over here because this looks like a difference quotient to me. So what we can do is we can artificially put in I'm going to multiply everything by j0 squared. I'm going to divide everything by j0 squared over here. Okay? And of course, that's what? This is going to be the derivative of y over j0. Okay? Such that x j0 of x quantity squared times this derivative, d by dx of y over j0, is a constant c1. So therefore, d by dx of y over j0, so that's of course j0 squared, just j0, yeah, j0 of x, is equal to a constant c over x times j0 of x quantity squared. Great. Now, of course, we know that this expansion over here starts over here at 1 And then the next one over here, when n's equal to 1, I'm going to have a -1. And then when n's equal to 1, I'm going to have an x squared over 4. So that's going to be an x squared over 4 minus x squared over 4. And so on. And so since it starts at 1, I know that its reciprocal has a valid Taylor expansion in terms of even powers as well, right? So this thing over here, the next thing to note, now, note, therefore, that d by dx of y over j0 of x is equal to c over x, and then 1 over 1 plus the sum. Okay, let's say k goes from 1 to infinity of some coefficients. Let's call them gamma k x to the 2k. Okay? And that comes from the fact that 1 over j0 of x, quantity squared, is equal to this sum. 1 plus the sum, k goes from 1 to infinity of these numbers, gamma k x to the 2k. Write down the Taylor expansion of that function 1 over j0 by using the quotient rule. Alrighty, good. And so now, what can we say? Well, we can formally integrate this thing over here, right? And so if we formally integrate this thing over here, what's going to happen? So we're going to have that y over j0 of x is going to be a constant, c natural log of x, and then plus some new numbers over here, plus some new numbers, because that when I integrate this logarithmic 1, plus some new numbers, 1 to infinity of gamma k tilde x to the 2k, because this x to the -1 is going to bring that down by 1, so I'm going to have to raise it by 1. And then we can multiply both sides over here, and so we can conclude that y0 of x, and of course there's another constant, let's call it, that's a c1, of course, that's a c1, plus another constant c2. So therefore y is equal to what? Y is equal to c2 j0 of x, that's the solution we know, and then plus c1 times all these things, there's a c1 over here as well, plus c1 times j0 of x times the natural log of x plus some analytic function over here, plus the sum, k goes from 1 to infinity of gamma tilde k x to the power 2k, x to the power 2k. And so therefore we explicitly see that this function over here, of course we can compute these gamma k explicitly, it just depends on the Taylor coefficients of the reciprocal of this function squared is. And so this function over here is sometimes referred to as y0 of x. So this is, our y is really c2 j0 of x plus c1 y0 of x. And this y0 of x is called the Weber Bessel function, Weber's function. And notice that Weber's function behaves like what? Weber's function has a log of x times j0 of x, so that's going to be a 1 times log of x. So this function goes to negative infinity as x tends to the origin. So this function exhibits the properties of a regular singular point at the origin because I have a logarithmic solution as my second linear independent solution of the Bessel equation. It's a logarithmic function embedded sort of in the analytic part of the function, so I have a singularity at the origin. Thank you very much.